right, ladies and gentlemen, good morning to you guys. Let's see what's going on here, and let's get to the web page. Let's scroll out. That's 262. All right, now let's go back to take a look at this here, right? We're looking at integration by partial fraction decomposition. And so, ladies and gentlemen, let's see here. We looked at linear factors, and I want to double check here, right? So this is going to be, if we look at the iPad, right? These are distinct linear factors. Oh, okay, we wrote it down right there. Okay. Distinct linear factors, and then, okay, distinct linear factors, this time with three factors. They're all three linear factors, right? So we're looking at that. So remember what we introduced. Here we go. Now it's a linear factor, and we introduced a quadratic factor. All right, so we know, okay, what happens when you have that quadratic factor? And then we're going to introduce, or they think we did a repeat quadratic. Yeah, repeat quadratic factor. So in other words, this is an exponential with a quadratic, right? The denominator, exponential, repeat multiplication, what they mean. Repeat quadratics, and then, let's see what else. Okay, we're at complete quadratics. So if I look at this sheet here, we said, okay, case one, you have a linear factor. The linear factors. We got to do repeat linear. I don't think we did a repeat linear. We introduced a quadratic factor, and then we did a repeat quadratic factor. So we're going to have to do try to look for a repeat linear, right? And let me double check. I think I do have some. Yeah, I do. I did a bunch of these. I have a bunch of notes over the years on this, from various years. So, and I think I put some online for you guys. So if you said, oh, what were these here? This is some examples, I think. Well, these are actually lectures, I believe. Okay, if you go back to the browser there, these were lectures there. And then these were examples from some notes I did years ago. I don't remember, So I remember just putting them up for people because I think people asked me at one point, they said, hey, can you put up some of those things? I go, sure, I'll put them up for you. And I did. So anyway, so we're talking repeat, right? Repeat linear. And so let's preface this. Repeat linear. So we'll give you an idea of what that means here. So you can have 1 over x squared, x minus 1 squared, dx. And we got to say hello to everybody. Let's see who's here this morning. We got Lely, Nguyen is here, Paula is here. Luke is here, and we got Jesus. Okay, you guys. We got people here in the room too, so all right. Okay, so you might say, what does a repeat linear mean? Now, if you guys take a look at this here. You can look at this first term two ways. I wrote it as a repeat linear. Right? So this term is repeated, this x term is repeated. You can think of it that way as x times x, right? And then you got this next term, right, x minus 1. And that's repeat. So this is why they say, oh, this is a repeat linear situation. Okay, so like the repeat quadratic, right? We looked at a repeat quadratic. So I want you guys to note how we do that. And your book's going to say something like this. Let's say what the book says. The book's going to say something like this. I'm not going to go back with that language. It's going to say for every repeat linear term, factor of the form, I guess ax plus b to the nth power, right? So in theory, you got n of those. Okay, so you have for every repeat linear factor of this form, you're going to use the following. Okay, I'm going to put this over that sum here. Okay, and this is a big A, A1. This is A2, and this is AN. So for every repeat linear factor, you're going to have to use this summation there, or this sum here. Now for both, you got 2. So I'm going to remind you guys, you might say, okay, what happens when you have 2 repeat linears terms? Right? So for each now, it says for each one, for every, I think your book says for each, but here's what I want to remark. I'm going to put this 1 over x squared, x minus 1 squared here, right? So this would be a over what? What is that? What does this language mean? You guys know? You start with the first power. Yeah, a over x. Good. And then put b over what? X squared. So you increase your powers. You start from the first power. And if it was a third power, you go all the way up to the third power. So I don't think they do that though, because like I said, they don't want to give you like a big system in theory to solve. But that's kind of how you would do it. If you had a third power, you go plus c to the x to the third power. You don't have that. Now they're saying do this for each. Because you have 2, we're now going to have to add a c now with x minus 1. And you increase the powers there too, right? So you're going to have to add that d now over the x minus 1 to the second power. So all this really means is increase your power to the number of times it is repeated. And you do that for each. I know I put for every, put for each. Okay? And that's kind of what you do. That's how you begin to set this up. Okay. All right. Now, ladies and gentlemen, here's kind of what we have to do here, right? What do we do at this point? Do you guys remember? In theory, like yesterday, I think I said to you guys, you're going to do some what? Some addition. You're going to use some algebra here, right? And remember, what's the LCM? If you're going to add fractions, what's the LCM? This is the LCM. Okay, you guys okay with that? This is the LCM. Now, your book is going to say something like this. Did anybody read the book and take a look what the book says? Here's what the book says. I told you guys yesterday, use algebra. Because when I took this course years ago, that's what you did. You added these. And this is going to be over, of course, obviously the LCM. Right? And so for me as a student, I used to look at this and say, you know what's going to happen is you actually write down what is missing for each term. Like for this a term over here, right? You see a over x. Like for me, it became something simple in the sense that I know what's missing. You know what's missing is the x and x minus 1 squared, right? And then I went to the next term, said, oh, what was missing? Oh, it already has an x squared, right? So I have b, I have that x minus 1 squared that's missing, And then the next term here with the c, you go, oh, that's going to have a c, x squared x minus 1, and then you got the d, and what's missing is just the x squared term, right? That's what I mean. But what your book says, the book says something like this: multiply both sides by the LCM. You know? Yes? Which one are you looking at? A? Yeah, because you know, the LCM is x squared, right? So what I'm saying is what you would do to get the same denominator for every term, like you'd say x and then x minus 1 squared here, x and what? X minus 1 squared, right? For that one. That's what I'm saying here. And then for this one, you say, oh, I need the x minus 1 squared. This is how you can add and get the like denominators, same denominators. And then same thing for the rest. So that's kind of what I'm remarking about. But if you like, it's the same as what the book says. Multiply both sides by the LCM, because what that does mean then, it's equivalent logic. But what we're saying is 1 will be ax, x minus 1 squared, b, x minus 1 squared plus that cx squared, x minus 1 plus dx squared. Okay, because remember yesterday we said the numerators will be equal. If they have the same denominators and you have fractions that are equal, the numerators are equal. And ultimately what that's really saying is that 1 equals the rest here, right? Now the fact that these have linear terms, right? You guys see what I'm saying here? The fact that these have linear terms, that's very nice. Why do I say it's very nice? If you have linear terms, you could use cases. Like first case, if x is 1, right? So if x is 1, you might say you put a 1 everywhere, you do. You know what you get if x is 1? What do you get? You should get d is 1. Is that right? So if x is 1, I can see automatically d will be 1, I think. Do you guys see d being 1 and x is 1? Right? Because doesn't that make all of these, these terms are going to be 0. 0, 0. So d times 1 squared is d is 1. So when x is 1, we get d is 1. So that's a pretty good thing to start with. So you go, okay, I got d is 1. All right, you guys okay with that one? Now, you say, what would you do next? Well, let x be 0 now. And do you guys know why I want to let x be these values? Can you guys see why we're going to use 0 and 1? Because go back over here, right? What would make that 0? You can say set x minus 1 equal to 0, and that means x is 1. Now, what would make this 0? Well, just simply x is 0. You know, so I can find values here. And so now if x is 0 everywhere, what I know is that this term is 0, this term is 0, and this term is 0. But what I have here will be 1 will be b equal to b, 0 minus 1 squared, or b is 1. You guys okay with that one? There it is. Now you might say, okay, once you do this, what can we do? Because it seems like we're out of options, right? So at this point, you might say, what can we do? We got the D and B values. What might we do? We might continue with cases. You can continue with your cases. You can now find a value of X that you could use any value of X now, but you're not going to get anything to zero out if I use a value of X now, again. Things won't zero out. So if I say to you, okay, let X be 2 now, right? X could be any number. It could be 3, it could be -2, it could be -1, it could be 1/2, So plug in X is 2, and you say, what do I get? I got A times 2, 2 minus 1 squared, B times 2 minus 1 squared, right? C times 2 squared times 2 minus 1 plus D times 2 squared here. So 1's going to be 2A, okay? Because 2 minus 1 squared is going to be what? 1. And that'll be plus B. And then you're going to get plus, looks like 4C, right? And you get 4D. Okay. So double check our arithmetic is okay, because it would be ashamed if we did our arithmetic wrong, right? And then you look at this and you say, you know what, Mr. Judge, I got one equation and how many unknowns? 1, 2, 3 unknowns, but not exactly, because what is the value of D? D is 1, B is 1. So 1 equals 2A plus 4C. Double check, is that going to give you 5, right? Or we can say 2A plus 4C now is -4, I believe. And divide both sides by 2, A plus 2C will be -2. Okay? So if you look at this, one equation and 2 unknowns in terms of A and C. Right? So here's one thing that we can do. If you want, you could continue with cases. Let X be now, you might say, maybe we let X be -2 now. Okay? Doesn't have to be -2. It could be any value. You probably, maybe you want to let X be 3. Maybe you want to stick with some nice positive numbers. It doesn't matter. But go back and see what kind of system you're going to get here. So 1 will be here. We'll say 1 equals 3. Okay, A times 3. Let's just be careful. 3 minus 1 squared, right? Plus B times 3 minus 1 squared plus C times 3 squared, 3 minus 1 plus D times 3 squared. Three minus 1 is going to be 2, right? You okay with that? 2 squared? B times 2 squared. C times 9 times 2 plus 9D. So I'm going to kind of let you guys see this here, and that's going to give you a 12A plus a 4B plus 18C plus a 9D. And you say, I get 4 unknowns and 1 equation again. Well, remember, B is 1 and D is 1, so that we get 1 is 12A plus 4 plus 18C plus 9. So we get 1 is 12A plus 18C plus, is that 13? Subtract 13. Okay. -12. 12A plus 18C. -2. 2A plus 3 what? C. Double check. Okay, haven't had all my coffee. Multitasking, reading about what's going on in the world. But the point I want to make here is you now have really the second equation. Okay, so double check. Did we make an error in any arithmetic? Did you guys see any arithmetic errors? No coffee yet in me. It's not going to kick in until an hour. So you might say, how do we actually solve this? I'm going to solve this by doing some beginning algebra. Okay. Negative 2a minus 4c is positive 4. 2a plus 3c is negative 2. So when you do your arithmetic, we get negative c is going to be, what's 4 minus 2? Is that 2? So what does that mean about c? What's c going to be? Looks like c is going to be negative 2. Okay, you guys okay with that? So using some beginning algebra. And then you say, well, how do I get the other value a? Remember how you get the a value? You're going to use what do we call that? It's back sub. So plug back in any of these equations, c being negative 2. So what I can do, even though, you might say, well, that kind of looks a bit odd. Not really. C being negative 2. I'm going to go back to that original equation. I can do that. And I get a nice a, but this will be a minus 4 is negative 2. Our a will be 4 minus 2. What does that mean about a? 2. Okay, so a is 2, c is negative 2. So as you guys can see, a lot of the work is just going to be setting this up for your what? Setting this up for your integration. We didn't even integrate yet. This is the Math 260, partial fraction decomposition. Just kind of curious, do you guys remember doing that in 260 or pre-calculus? Because your 260 instructors tell us that you guys do. They do. They say, yeah, we do that, because we will complain, we'll tell those instructors, hey, make sure you do partial fraction decomposition. B is 1, D is 1. So let me go back to the original, if I can find it. B is 1, D is 1. Let's get rid of all of that stuff. B is what? 1. D is 1. And you need to get A and C. A is 2. C is negative 2. So that integral really is what you see here. 2 over x, 1 over x squared. I'm going to do this. I'm going to say minus that 2. Okay, and you get plus that 1 there. So which gives you, by the way, if I use properties of integrals, 1 over x dx plus the integral of 1 over x squared minus 2 integral 1 over x minus 1. And then we'll say, hopefully you get some space here. Plus the integral of 1 over x minus 1 squared dx. So how many integrals is this, ladies and gentlemen? This will be 1, 2, 3, 4 integrals. 4 integrals there. So if there's 4 integrals, remember what we say, what do we use? Well, this one you guys should know. You should know this one. This is actually, if you want, we can write this as, I didn't want to erase that. I wanted to erase this, x to the minus 2. This is going to be what? U sub, and this is also going to be a what? U sub. And so to let you guys know on the final answer, I'll give you guys a final answer. 2 natural log absolute value of x, right? Minus 1 over x, minus 2 natural log absolute value x minus 1. This will be minus 1 over x minus 1 plus that c. Right, there you go. And you know, you could use some properties with the natural logs. You don't have to, but you could. But I just wanted to let people know and to see every integral where it came from. This came from here in orange. This is in green. We got gold, and then we got pink. So we did do, you know, we did do a case of all of these here that you can see. Let me just see some more that I have. Anything that looks interesting. All right. I'll give you guys another one here. Maybe you want to try this one. I don't know. Should we have you guys try this one out? What do you guys think? Have you guys tried this one out? Have you guys tried this one? See if we did this one. I don't know if we did it. We're going to try to figure out what this is. Okay. Notice what you're looking at. I don't think we've done this one. Have we? I think we did. Did we? No. I don't think so. It's possible. How would you guys describe this if you said to yourself when you looked at this? What would you describe it as? This portion is linear, is that right? So I'm going to say, you're going to call this what? Repeat what? Linear. Okay, there's a repeat linear. We know what to do with that factor. And then this is going to be a, what is that one called? It's a quadratic. It's not a repeat quadratic, and it's only one quadratic. Is that right? So it's good to look at those and go, oh, okay, you got that. So in other words, the x squared minus 2x minus 1 over x minus 1 squared, x squared plus 1, since the first term is repeat linear, we'll put a x minus 1 plus what? B x minus 1 squared plus cx plus d over x squared minus 1. Now, I want you guys to note, we're gonna try to do what the book says. The LCM, if you were to do the algebra on the right side, the LCM is x1 minus 1 squared, x squared plus 1. Your book says multiply the left and the right side by this term. So they want you to multiply the left side and the right side by this term. What that does for you is, On the left side, you're just going to have the numerator, right? So I say, hey, do the algebra, right? What I mean is add those sides and then use that fact I gave you that you have fractions that are equal means that your numerators are equal. Well, this is exactly the same thing. If you multiply both sides by the LCM, on the left you have the numerator, and then on the right you have a. Now tell me what's missing from the LCM. A factor of x minus 1 and x squared plus 1 for the a term. You guys see what I'm saying? Because if you multiply this term here, this first term, by the LCM, what you have for cancellation is one of those x minus 1 terms, really, right? And that's, like I said, this is how, it's the same equivalent kind of thing. Remember, you distribute. So this is going to be plus b, and you say, wow, what's going to cancel here now for the b term if I multiply by the LCM? Well, very simply, x minus 1 squared. And so what are you left with? The x squared plus 1. And then you have plus, and you go, okay, cx plus d, right? You got that x squared plus 1 term, right? You say, well, okay, I got the cx plus d now. What would cancel? The x squared plus 1 now, and you're going to be left with the x minus 1 squared. So that's kind of like I said, you know, you go through that and you notice that this term will cancel. The denominator, x squared plus 1 will cancel. All right, you guys okay with that one? And that's kind of the equation you get, your x squared minus. And then you might say to me, okay, what would you do now? Since I have a linear term, right? Maybe you think, maybe we should try cases, right? What happens if x is 1? Right, what do you get when x is 1? It looks like we get the following, right? Let's be careful. We get, on the left side, 1 squared minus 2 times 1 minus 1 will simply be, looks like it's going to be b 1 squared plus 1 because the other terms are 0, right? Is the other term 0? Yeah, it's going to be 0. So 1 minus 1. So it looks like we get negative 2 becomes 2b. And what does that mean about b? b is going to be negative 1. Good. And then now you might say, but you know what? There are no other linear terms. Okay. Then start using values of x. All right, so I'm going to say start using values of x. So you might say, okay, you know, one of my favorite values of x to use is 0. The reason I like 0 is because it makes your computation easy. Do you guys know what I'm talking about? It just makes your computation easier. So you'll have 0 squared minus 2 times 0 minus 1, a times 0 minus 1, 0 squared plus 1. Now I'm going to have to add some values here, right? b times 0 squared plus 1 plus, okay, is it c times 0 plus d, 0 minus 1 squared. So double check, ladies and gentlemen, because, all right, so a, that's going to be negative 1, that's going to be negative a, right? Plus b, and that's a parentheses, by the way. And it's going to be plus what? Plus d, I think, right? And what was b? negative 1. So that means 0 equals, well, I'm not going to put the 0 yet because you might want to say, where did that come from, right? Negative 1, negative a minus 1 plus d. Get rid of these 1's. 0 equals negative a plus d. What that means is a is the same as what? D. So if a is the same as d, that's the information we got by letting x be 0. A is the same as D. So what you guys can do again would be something like this, x squared all right. Well, I'm thinking of something that can be done, but let me see. Yeah, I'm thinking of something. Take a look at this here, right? Anyway, what do you think you might want to try here, ladies and gentlemen? Tell me if you're looking at this, you can try other values, x is 0, x is 1. You know, I'm seeing something here I might want to try. A is D. You know what I might want to try? You can get another value of x, and you start to create a system, and if you keep going, you could keep creating these values of x, creating systems. But you want to know what I'm interested in seeing here, right? You have 0x cubed here, right? Do you guys see what I'm saying? 0 times x cubed. You don't have an x cubed term. But if I multiply here, where would I get an x cubed term? I get x cubes here if I did some algebra. You guys with me on that? In fact, let's see what they would be. I think you end up getting just a, isn't that an ax cube? Is that right? Double check. I'm not going to do all the FOIL there. I'm not going to multiply every term. I'm going to multiply the terms. The first terms in FOIL would be x cubed, right? So then that's a times x cubed. So I don't care about the other terms. And then you got over here, you go, so what do I have here? Well, if I multiplied here, I mean, maybe I'll put x squared minus 2x plus 1 for this term. But similarly, I think I'm going to get a cx cubed. Is that true? See my point? If I just multiply those terms. Now, what that implies, ladies and gentlemen, is a plus c is 0. So does that help me? Maybe it doesn't even help me. Does that even help? All right, well, maybe it didn't even help me here. I got this. B is negative 1. I got A is D. I get A plus C is 0. You know what else I might do? Without having to do all the algebra, what is the last terms? Isn't the last terms if I do this? Maybe this helps. See that constant? If I did FOIL, isn't my last term here going to be a negative A here? And my last term here will be a B. I'm going to put that in orange. Double check. Okay? And then my last term here, I think, will be a D. Now, I hope I don't really mess this up. Just kind of, I'm doing a combination, right? So if I had to multiply this cx plus d times the x squared minus 2x plus 1, I think that last term will be just a d. All right? I think so. So what does that mean? Negative a plus b plus d Here's my equation. And I got b is negative 1. So let me bring this down. Okay. What's up? You could. Well, I don't know. Do you get a is equal to d again? Maybe you do. Maybe you do. This is what you'd be going through, right? Let's double check. B is negative 1. Okay, so there is, you can do, I'm going to say you could do something here that I want to remark about, but I kind of want to avoid, I don't know if I want to get, you got 4 equations and 4 unknowns. That's a system of 4 equations and 4 unknowns. So you can say here, d plus c is 0, b is negative 1. Here's what I think you can do. See from this equation? Let's double check here, okay? Tell me if this is okay. Negative a plus b plus a is negative 1. What did I do? And b is what? Negative 1. I got 0 is 0. Did that help me? No, 0, 0. So what would you do? Okay. D plus c is 0, or d is negative c. Well, what you can do then is maybe you want to take another value of what? Of x. So what value of x should you take? Right? Can I go back and erase all this? So maybe you say, I want to go back and do another value of x. I don't want to use this if I do that, though, right? So maybe you want to say, what would you guys say for x now if you wanted to do that? Let's copy that. And we say maybe x is going to be what? If we let x as negative 1, would that screw you guys up? What do you guys think? You could let x be 2. You could let x be whatever you want. So maybe we'll let x be 2. We'll stick with positive numbers. All right, let's try to crank this out. Here we go. 2 squared minus 2 times 2 minus 1. A times 2 minus 1 is 1, right? So I'll write every detail. It's too early. And then you get c times 2 plus d. 2 minus 1 squared. 4 minus 4 minus 1 is a times 5 plus 5b plus, is that 2c? Plus d times 1, right? So this says 2c plus d. So this means negative 1, ladies and gentlemen, is going to be what? 5a plus 5b plus 2c plus d, or I'm going to write it this way. 5a plus 5b plus 2c plus d is negative 1. So remember what the value of b is. What's b? All right. So 5a. I'll put every term. Minus 5 plus 2c plus d is negative 1. Or we can say 5a plus 2c plus d equals, I think that's going to be 4. Is that true? All right, now let's bring everything down that we know. So notice what this means, though. This tells you that a is negative c, just so you guys know. Is that true? If a plus c is 0, does that mean a is negative c? That also means d is negative c. Since a is d, so I'm going to put it this way. This also means that it's d, right? Okay, so what do you think you could do here? Do you guys think you can see something there? I see a little bit of something. Huh? So we have b is negative 1. I'm going to show a here is 1. C is negative 1. D is 1. You're going to find some of these values, right? So how do you use that? I'm going to suggest you guys do some substitution. You can say that 6d plus 2c is 4. Let me double check here. Let's do something here. See if you guys can see that there. A is d, right? 6d plus 2c. Well, sorry. I did that too fast. 5d plus 2c plus d is 4. 6d plus 2c is what? 4. Is that true? And what do you know about c? Isn't that c is going to be negative d, is that right? Six d minus 2d is 4. So that means 4d is 4, or d is, in fact, 1. So if d is 1, you could use all this information now back here. D is 1, A is 1, C will be negative 1. Anyway. All right, so it's just a substitution. But anyway, A is 1. Let's go back. A is 1. B is negative 1. So you say A is 1, B is negative 1. C and D. C is negative 1, D is 1. So C is negative 1, D is 1. I'm going to say plus a minus x plus 1 over x squared plus 1. Now you can factor out that negative 1. Okay, so you have 1 over x minus 1 minus 1 over x minus 1 squared, and that's going to be 1 over x minus 1 over x squared plus 1, right? You factor out that negative 1 there. And then I'm going to say to you guys, pay attention to this integral. We seen that yesterday. What did you guys see yesterday with this? You guys remember? What do we see? Anybody remember? What did we see before, right? You want to split this one up? You put x over what? X squared plus 1 minus 1 over that x squared plus 1. So remember, we're supposed to integrate all this. And then what's the deal? Here you might say, these are all now easier to do. This is u sub. This is a classic u sub. Isn't this inverse tangent on the right side? Do you guys remember? Inverse tangent all the way on the right? So like I said before, a lot of these integrals are going to show up again over and over again. You're going to see this and go, oh, okay, I remember that integral. Anyway, these show up. Natural log, absolute value of x minus 1. This is a u sub. Remember that one? A u sub. You can get plus 1 over x minus 1 minus 1/2 natural log x squared plus 1 plus inverse tangent x plus c. Yeah, can't draw. All right, should we try the granddaddy of them all? No, should we try one more, or we should move on to the next section? One more, the granddaddy? You want to do a granddaddy? Should we have you guys try that one? Oh my God. This one, in all honesty, I don't know if I'd ever give this one on a test because it takes long, but, you know, who knows? I'm going to see if you guys can read through what I'm talking about here, right? I'm going to give you guys this one here, right? X squared minus 3x plus 7, everything over what would you call this one? This one is a repeat quadratic, right? Repeat quadratic. So if it's a repeat quadratic, you go, oh, okay, I got x squared minus what? 3x plus 7, everything over x squared minus 4x plus 6 plus x squared minus 3x plus 7 over x squared minus 4x plus 6, and this is raised to the what? Second power. And I guess we don't have to put a parentheses here. Oops. Yeah, I mean, let me do this. I'm going to say this is the function r of x. Oops. Right, so that function, we're going to increase the power. Now, what do you guys use for constants? Ax plus b, and this is going to be now, because these are quadratics, and you're going to have a linear term, 1 degree less. That's kind of what that is. And then you say, I'm going to multiply both sides by the LCM, or in this case, just x squared minus 4x plus 6 squared, really. And what that means is you're left with the numerator on the left side. So you're left with x squared minus 3x plus 7 on the left will equal, now remember what's going to happen. You have ax plus b times a what? Factor. X squared minus 4x plus 6, right? Plus 6cx plus d. All right, you guys okay with that one? All righty. Now you might say to me, okay, what would you do here? I'm going to kind of remark about this here. I'm going to let you guys know something here, right? I'm just going to note, you don't have linear terms, so you can't zero things out. Okay, you can't zero things out. I can already look at some of this and say, I can tell you what A is. A automatically is what? A is 0. How do I know A is 0? Yeah, because AX, that first term when you do FOIL, AX cubed is going to be, and then you have over here like a 0 constant x cubed because it's not there, right? Plus that. So I know A is 0. Okay, and then I could even go further. I also know B is 1. How do I know B is 1? Because if this is 0, when I multiply here, isn't that a bx squared? And I don't have any other b term, or I don't have any other x squared term. So then that b value here corresponds to the constant that's here, which is 1. And then you might say, well, how do I go further with this? Well, isn't this going to give me, if I multiply this out, I get bx squared minus 4bx plus 6b cx plus d. So what I'm going to get here now is I know something else. D is 1. Oh, is D 1? No. Well, hold on. I may know what D is. Hold on. How do I know what the constant is, right? Let's go back here. Here's 7. You might say, Mr. Judge, that's D is 7. And I'll say, no. We have what? 6B, yeah. So you might say that 6b plus d is 7. where b is 1. So that means d is what? 1. And then you might say, how do I know what c is? Let's be careful. Let's change colors. Cx, negative 4bx. That has to be negative 3. Is that right? So you can say negative 3 is negative 4b is 1 though, so it's negative 4x plus, hold on. What do we do? Nope, we don't have the x's. Let's go back. We want to make sure, let's write everything down, right? It's always helpful, just write it all down so you don't make a mistake. Let's double check. Negative 3 minus 4b plus c, where b is 1. Oh, what's that? Oscar says, where did you get 6b plus d is 7? Oh, okay, Oscar. Oh, right in here in orange. See, the left side is equal to the right side. 7 is a constant. So that 7, if you want, maybe I should have kept it this way, right? That 7 on the left is going to be the same as 6b plus d, because those are constants. So it's in orange here. We're multiplying the terms. Once we found that a is 0, that made everything easier. And that now we can find that. So this is where I got the 6b plus d is 7 here, okay? And I'm doing the same thing in green with the x term. On the left side, negative 3 will be negative 4b plus c. And then you can actually solve, because this becomes, what does c equal then? C is 1, is that true? So in orange, that was the constant term. In green, that was the x term. And I would say to you, the key was that first a value being 0. That means if a is 0, you can zero out that term, ax, and you're just left with the b. And that gives you a very nice quadratic, or not quadratic, it gives you a very nice distributive property question where the left side equals the right side. You know, so that's where that 7 equals 6b plus d comes from. A is 0, b is 1. A is 0 and everything else is 1. So if you go back and you said, what does that mean here? A is 0, 1, 1, 1. So what does that leave you with? 1 over x squared minus what? 4x plus 6 plus x plus 1 over what? X squared plus x squared minus 4x plus 6. Double check. So if you kind of look at it this way now, you get 1 over, use your properties of integration. X squared minus 4x plus 6, that's a dx, plus the integral of x plus 1 over x squared minus 4x plus 6 squared dx. So what I would say now here, you have one integral and you have maybe 2 or 3 integrals. You can write this one, you can split up this integral in green into 2. if you like, you can split that up. You know. But I kind of want to give you a remark here. This one can be written if you want to do it that way. I think it could be done different ways, but let me do this for the green. X over, what is that? X squared minus 4x plus 6 squared dx. And you can do this if you want. 1 over x squared minus 4x plus 6 squared dx. So that both of these here are in green. So then if I asked, what would you do here? Give you guys a big hint. What would you do with that one? And even to some degree, these here too. Right? What would you do? Have you ever seen anything like that before? 1 over a quadratic. Yeah, exactly. Complete the square. Exactly. Right? Remember this stuff? You're going to complete the square and use u sub. And what would that give you? That would give you probably a inverse tangent function to some degree, right? It'll give you an inverse tangent. Because when you complete the square, you're going to end up with that inverse tangent for that one. And if you said, what if I complete the square over here for these? Well, I think it would turn into, in all honesty, for these two, a trig what? Substitution question. Because you're not going to get the inverse tangent for these because you have a power what here? 2. Guess what I'm saying? So you can split that up into 3 integrals. You know, I can even let you guys know by completing the square. X squared minus 4x plus 6 will become something like this, I think. X squared minus 1 squared, parentheses, plus 2. You know. So, you know, A is going to be the square root of 2 in you know, you'll see A is the square root of 2, but that's kind of how I'd say to you guys to go about it, because of the fact that unlike a test, that kind of doesn't become a good test question, because then you're like spending 20 minutes on one question when you want to have other questions to be answered. But I don't know. That's how I've seen some of these questions when you start to get these you know, down to here. You know, it's good to do. It's not saying, I'm not saying it's not good to do. It's good to get that exercise into knowing how to do it. But, you know, if you say on a test, when you have 10 questions to answer, you don't have like 20 hours to do it, you know. At least that's how I see it. That's my personal feeling. Like I said, I'm going through this pretty slow in a way, but it still takes some, you know, it takes time to go through that. But yeah, that first one's going to be an inverse tangent with u sub. The second one, you're going to get like a nice trig integral, trig substitution, which reduces to a trig integral, blah, 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 blah. So these are kind of all separate on their own questions, you know. So unless you thought to yourself, you said, okay, I'm going to give a student this question on a test. This is kind of how I think of it as an instructor. That one question really counts as what? Almost like 3 to 4 questions, you know. So you can do it, but, you know, then you're going to say, well, this is one question that counts as 3 or 4. So then you reduce all the others. That's how you balance it in my mind, how you would balance that out. Because you go, hey, I got this first part, partial fraction decomposition. If people can get that part correct and get these constants, good. They should get credit for that. You guys know what I mean? And then after that, they get 3 integrals to do. Then you grade those separately with their own credit. Do they do it, the complete the square correctly? Do they do the others? Do they do the trig substitution correctly? Now do they do the trigonometric? So I don't know. I never felt like giving one question that was long is a very good question. That's just my personal philosophy. It's good in some sense if somebody had extra time to do it and you had them do it on their own separately. Then that's a really good question to do. But is it good in a short time frame to ask when there's a lot of other things you can ask? But I have other colleagues who say, you know what, the reason this is a good question is because it has partial fractions, is because it has trig sub, and is because it reduces to a trigonometric integral. So you're really testing people on those 3 sections, And I understand their point, but I don't know if I would, that's kind of personally for me what I think is it's good to do if you know how to do all the other stuff, Yeah. Yeah, it's Tuesday, I think. It's a Tuesday. Did I have the wrong date there? I might have had the wrong date. I'll change the date, yeah. And I think somebody said to me it's worth 150 points, and it's like, no. Yeah, I know. You know what it is this, believe it or not, as technologically, people think I'm advanced technologically. And I would say, not really. What happens as you get old and you become an old man, right, is everything, it's true. Everything now becomes a chore to do. Even this is a chore. All of this, believe it or not, it's just completely a chore. So if you see me in the mornings here going through all the nonsense I'm doing, you go, what is he doing? He's getting everything ready, and it's a chore, and handling 500 things at one time, and, and then the date's wrong, huh? Is it 29th? Okay, let's change that there too. So yeah, all in this technology too, it's not as intuitive as it used to be for me. And that's either that I'm getting old, or it is, what? That's an old man issue, or it's something else. Maybe technology isn't just, the people that do technology just aren't as intuitive with everything as they used to be. And it might just be because things are more advanced and more open than it used to be. So a lot of things, I can't even text correctly, in all honesty. Even texting is a challenge. Right? I know that autofill drives me crazy, and my fingers can't never touch the right buttons. I send all kinds of insane things to people that don't even read right. And that just might be normally what happens. I don't know. But I look at it and I'm like, is it an old man thing, or is it just technology, or both? It's probably both. Yeah, I'll put a study guide for you guys, in all honesty. I'm going to put a study guide there. Yeah, I'll do it today is what I'll do. I'll get it to you guys today. I did the statistics classes yesterday. Now I'll tell the intermediate algebra to do them today, and so on. But yeah, I'll get it out, study guide. But yeah, I don't know. There's some things I have to think about. I don't want to say, because I don't want to commit, but there's some things I have to really think about in some ways here. But it's all good stuff. I don't know. I think we want to talk about, we'll take a break. How's that? You guys want a break? Give you guys a quick break. And where is my clock here? Yeah. All right. We'll give you guys a nice break to get some coffee. All right, ladies and gentlemen, we are back. Let me do a few things here first. Yeah, I'm going to do that here first. Let's go to, forgot to do this here, 7, 2. We'll say we'll give you guys some odds to work with. And then here's what we'll also have. It's a simple kind of thing, but we're going to have to go back and remember a few things from Calculus 1. So let me see if I can find it. Well, I'll find it here in the Calculus 2 worksheet. I don't know if you guys recall. We'll work with this, right? So let's see what I kind of developed here. Oh, yeah. Oh, yeah. Oh, I guess I have to talk about these. I thought we did this in Calculus 1. Do you guys remember? Left endpoint, right endpoint, midpoint approximations. That's my memory. So this is going to be left endpoint, right endpoint, midpoint approximation. Yeah, so this stuff was in Calculus 1, but let me go back and express this to you guys here in the iPad. Okay, because we did that in Calculus 1, but you might say, what is this all about, right? Well, for example, if I said to you guys, I want you to integrate something like this. E to the x squared dx. And that's going to be over this interval from 0 to 1. Okay? So think about how what we've been doing is looking at techniques of integration. But what you may not know, you may not realize, is you cannot integrate. Okay? Now, we know what that curve looks like. You know, if I said to you, I can tell you what that curve looks like. If I go to Desmos, y equals exponential function. E to the what? X squared. Okay? And I usually don't like red. Purple's fine. But we're going to try to integrate from 0 to 1. So if you said, what does that really mean? Well, x is 0. It's one boundary. X is 1. That's the other boundary, and the y-axis. So if you're really going to be technical about this, this is kind of what we're trying to find. Area under the curve from 0 to 1. If you guys remember that, e to the x squared. So there is area under the curve, right? You guys see what I'm saying? You have some area. So the question is, what is that area equal to? Right? Area under that curve here. So I can kind of do a real rough sketch. You know, and the irony is, doesn't it kind of look like a parabola? I'm just kind of remark. It's not really a parabola. This is x is 1, x is 0. So if you guys recall, we did do some area under the curve for Calculus 1. But the problem is, you may not realize this. It goes beyond the scope of our course, and I won't go into some of those details. But the problem is, everything that you see here, we've done a lot of techniques in integration. And those are kind of the known techniques. There are other techniques. We can spend the whole semester really on techniques of integration if you guys really wanted to know. Your book does dive deep into some of these other techniques. I've gone over some in the past. You know, I have to weigh really what to do, what not to do. So there are some techniques that you can do, but you can't integrate this one. There's no known technique. So this is what's called a non-elementary function. And we have no techniques to integrate these functions, meaning we don't have techniques that are based on algebra. You know, we don't have processes that can integrate e to the x squared. It's a classic example. But we know there is an area there. So when there is no known techniques of integration, like in Calculus 1, you guys remember what we do? We what? We approximate the area under the curve. Okay? And that's going to be over the interval from 0 to what? 0 to 1 here, right? Over this particular interval. So I don't know if you guys remember Calculus 1 stuff on that. Do you guys remember how we did that? I'm just curious. We looked at that Riemann sum. Anybody remember? This is where that approximating rectangle came from. So in Calculus 1, we had that delta x, right? This is the approximating rectangle, if you guys recall. And the area of that approximating, since it's a rectangle, it's length times width, right? So that area will be the length for some x value. And that's your f of x, by the way. And that width is the delta x. So just going back to the Calculus 1 techniques here, getting that area of this rectangle. And then you say, well, that area, if you guys recall, we always partition. So let me really go into that detail because this is kind of going to come back for us. Remember how we always start with this? They always say partition the what? The interval, and they describe it in general, AB, into n subintervals. So this is Calculus 1 language. Into n subintervals of equal length delta x. And you say, oh, is that partitioning this interval here? Yes, it is. Okay, so you have this partition. I'm going to do a close-up of it. Here's A. There'll be x1, x2, x3. Then they have xi, I plus 1. This is xi minus 1. And this will be well, we'll say this will be ultimately b. Or you'll have an n minus 1, and this will be the b term. Okay, so they're taking that interval, like in this case from 0 to 1, you partition it into n subintervals, if you guys remember. Right? And remember the formula for delta x? What's the formula for delta x from Calculus 1? It's the length of the interval divided by what? Divided by n. So this is back a numerical technique. There's only going to be one numerical technique I talk about. It's probably the numerical technique for integration. You don't see it in Calculus 1, you see it in Calculus 2. Calculus 1, you have the left endpoint, you have the right endpoint, you have the midpoint, and I've given those in the Calculus 1 setting, but in Calculus 2, you have really Simpson's rule, the only real rule you guys want to see. Now, I go through this because in some courses that you take, like even programming courses, they're going to expect you to know Simpson's rule, you know, because they might ask you to write a program to do it. So remember, this is the interval AB. It's partitioned into, every one of these has a delta x length, right? Delta x. And so you partition this into n subintervals. This is your x naught as well, and this is your x1. So if you remember here in this sheet, I actually do a better graphic. Let's do a close-up of everything I'm talking to you about. And you know, that's kind of what you're seeing, but this is a left endpoint approximation called L1, so that was back in Calculus 1. And then you had the visual of that. These are the approximating rectangles, if you guys remember. you're going to add n of those, right? And so what you do here now, as you add n, you have this is the formula now. Right? You're adding rectangles there, each represented by f of x1, f of x2 times that delta x. And so you could do some algebra, and ladies and gentlemen, you get that integral. And that's the formula you guys use for the left endpoint. And then similarly, you might say, well, what's the other technique you learned? Well, you could use the right endpoint. And then here's a graphic of the right endpoint, approximating rectangles. You add all those rectangles from calculus 1 and you get your formula for the right endpoint, if you guys remember that. You know. And then you might say, well, what is that midpoint? Remember, the midpoint was the more accurate of the three. More accurate. You got to the area a lot faster. So it's just the midpoints of those intervals. When I called them M1, M2, there's a picture of midpoints from calculus 1. And then you do the same formula, and now you have the midpoint formula to approximate area under a curve. So those worksheets you guys can take a look at and consider. Now today you want to say, well, what do you do in calculus 2? We have what's called Simpson's rule. Simpson's rule. Now your book demonstrates the formula for Simpson's rule. So you can look at the book and read that. We call that SN for Simpson's rule. But it's just a numerical technique to integrate. So you're going to partition your interval, and we'll do that. I'm going to show you guys how to do that. Probably the most work is in the partition. But it's going to be a formula just like the others. And the formula, you might say, what is the formula? Well, I think I proved the formula. I don't remember. Let me double check. No, I gave it here. Here's your Simpson's rule formula. Okay? It's called SN, and you have the delta x over 3 times 1, 4, 2, 4, 2. These are weights. It's functional evaluation. And you go from x naught to xn, I believe. I've got to double check if there's a typo there. But you also want to let n be an even number. You have to have an even number of partitions, I believe. So we're going to go through this exact formula that you guys see here for Simpson's rule. And it's a pretty fun rule. You just use your calculator. We're going to see that. Yeah, I think I'm good. Yeah, you got the midpoint to give back to you guys there. Okay. Right, n is even here. So let's go look at an example of this, okay? Here's an example. They're going to want you to integrate from 0 to 1, e to the x squared power dx. And they'll say use Simpson's rule with n equals 10, okay? Notice what you must have is an even number of partitions. That's the assumption. Okay? So they're really asking for this question. They're going to say, what is S10? Okay, because Sn is defined to be delta x over 3. I'm going to write this down for you guys here. Okay? F of x naught plus, now go back and take a look at the formula. You see how you start with f of x naught, and then what happens? You got 4 f of x1 plus 2 f of x2 plus what? 4 f of x3 plus 2 f of x4. And that goes all the way up to, and I want you guys to pay attention, right? What does that go up to? 2, what do we got? 2, yeah. Notice this goes up to the ending part, which would be 4. Okay, I'll do 2. F of x n minus 2 plus 4 f of x n minus 1 plus, and that's going to end this way, f of xn. Okay, so let me clean this up. Where are we at here? Yeah, I guess I have to do it that way. I hate that this doesn't have enough space. Now, I want you guys to pay attention to this important detail. I'm going to put a 1 here, and I'm going to put a 1 here. You can always remember this formula by remembering the sequence of numbers here. Okay, those are called weights, by the way. Those are weights. The weights here is a sequence. 1, 4, 2, 4, 2, forever, 4, 2, 4, comma, 1. Okay, so when I wrote this down on that sheet for you, remember the weights, because that's going to be an important detail in your formula. Right? You got these weights, 1, 4, 2, 4, 2, 4, 2, blah, 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 2, 4, 1, you know, ends that way. So it alternates between 4, 2, 4, 2, 4, 2, 4, 2 until you get back to the 4 and then a 1. So you're going to have an even. And that worksheet's on the website, so you guys can have that, you know, for you guys, right? Now, the rest of this, if you say, what's the rest of this? Okay, this is x naught, x1, x2, x3, x4, xn minus 2, xn minus 1, xn. And ladies and gentlemen, this is the f of those things. So this is functional evaluation. This is functional evaluation, ladies and gentlemen. So that's the beauty of it. So let me remark here. Here's your first step. You need delta x, and you need these xi's, or these x0, x1, right? So the most of the work comes in the partition. So when they say to you to partition the interval 0, 1 into n is 10 subintervals, right? Delta x is 1 minus 0 over what? 10. You say, why is that 1 minus 0? Do you guys know? In this a and b, and then you know n is what? 10, so you're going to use this formula. b minus a over 10. So your delta x, by that calculation, is 1/10, or really 0.1. Okay, you okay with that one? And I really don't like this example having 10, but bear with me on that one. Okay, I'll show you what I mean. So this is the first part we want to get in gold, the delta. Now, S10. Okay, so this is the delta. This is going to be 0.1. And then you might say, well, how does the partition work? You guys remember what you do? Where do you start here? This is 0, right? And so the next point, this will be x naught, and this will be x1, x2. Do you guys, how do I get the next point? Do you guys remember? Add the delta x. That'll be what? 0.1, and then 0.2. Good, and then 0.3, and then, yeah, remember that one? People kind of like numerical integration. They liked it so much that on a test, when they couldn't integrate, you know what they did? They go to numerical, you know. So these are this is xn minus 1, this is xn. This is the partition that they're talking about. You guys have all those values here, okay? And that's what you guys need. And let me go back here with these last two, because really, if there's 10 partitions, this is going to be an x what? 9 and an x10. So this is going to become, remember the formula? This is f of 0. That's the x naught. You guys remember? What's the sequence? 4 f of what? 0.1 plus 2 f of point what? 2 plus 4 f of 0.3 plus 2 f of 0.4 plus 4 f of 0.5, right? Now just alternate between 2 and 4. F of 0.6, 4, f of 0.7, 2, f of 0.8, 4, f of 0.9. Notice you ended with the 4, and what's this one? F of 1 is just going to be what? Yeah, the weights. So in other words, pay attention to the weights. This is 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, and then this is going to be a 1. So it's always going to follow that sequence if you have n being even. I can't remember, I think they have to have it bigger than 2 type of thing, whatever. But typically people look at 10 partitions, you know. And so you say, well, what about the rest? Well, what is delta x? Delta x is 0.1. And then you might say, you know, Mr. Judge, what in the world is a function anyway? You guys remember what the function is? It's e to the what? X squared. So we want to know about this very, very famous numerical approximation formula. 0.1 divided by 3. E now to the what power? 0 squared, because that's the function, right? Plus 4 e to the 0.1 squared. Plus 2 e to the 0.2 squared. Plus 4 e to the 0.3 squared. Plus 2 e to the 0.4 squared. Plus 4 e to the 0.5 squared. Right? Plus 2 e to the 0.6 squared. Plus 4 e to the 0.8 squared. Did I miss 7? Good, I didn't mess up. I'm going to get that there, right? Plus 4 e to the 0.7 squared, right? Plus 2 e to the 0.8 squared. Plus 4 e to the 0.9 squared. And then plus a e to the 1 squared here. So what I want to say to you guys is this is essentially what you enter into a, you know, calculator or into a spreadsheet. You know, this is kind of like if you take some programming courses, they're going to ask you to write a program with that, you know. So that's kind of why you want to give people that formula and remind them about the numerical approximation, because other classes will have you do these things. And like, for example, you might say, I just spent money on a fancy dancy calculator, right? And like a TI, where's the TI here? I'm going to get the TI. TI is coming up. And some of these calculators can do numerical approximations. You guys know there's some software does it, and calculators do it all the time. And you might say, well, how do they do it? They probably have Simpson's rule in it. You know, that's what's behind the scenes. They got Simpson's rule. So, you know, again, you kind of want to teach people in these STEM formats how to do numerical approximations, because they're everywhere. Because the truth is there's more functions in this world that you can't integrate than ones you can. All the ones that we integrated were all very specially chosen. You know, these are specially chosen. The ones we just integrated. They're not, ladies and gentlemen. If I randomly put something down on a piece of paper and say to integrate it, you probably can't do it, because there's only so many known techniques. You may think there's a lot, really only studied a few. There are others. You take math courses, there's other techniques, but other math classes, but generally speaking, can't integrate things the way you would like. You could get a PhD in these methods, like approximation methods. So you might say, well, what do I do on a calculator with this? Well, what I would do is something like this first. You know what? What is e to the 0, by the way? Isn't that 1? And then this is just going to be the number what? E. Is that right? 0.1 divided by 3. Okay, I guess I'll take that. That's 1/10. That's really 1/30th. But whatever. Okay. So you might say, I'm going to put 0.1 divided by 3 times now. You see the parentheses there? Right? Maybe you want to scroll in. And then now what am I going to do? I'm going to enter all of the what? The first term was what? 1. So this is going to be, maybe I have to scroll out. I don't know what you guys prefer, scrolling in or scrolling out. 1 plus, maybe you put 1 plus, then we need E. You know what E is? Where's E? Second, there we go. E to what power? This would be 0.1 squared, okay? Now you might say, how do I get out of there? Use this arrow key. And let's see, plus, oops, did we make a mistake? No, we did make a mistake. What do we have to do? Right, so you say, okay, 4 E to the what? 0.1 squared. And you go, well, how do we get rid of that other one? I think I have to do a delete. Delete, right? Go back here. Delete. Delete. So it's easier for me if I scroll in. So hopefully you guys can see that and use your calculator because, you know, old man Judge here is blind. Right? Hard for me to see now. So I'm going to have to scroll in just to let you guys know. And is that even a 0.1? I think so. Okay. Now you say, what is the formula going to be? Plus 2e, second e raised to the, it's already in the power position. Is that going to be 0.2 now what? Squared. Come out of there. Plus 4 e raised to the point what? 3 squared. Come out of there. Plus 2 e to the 0.4 squared. Come out of there. Plus 4. Where's e? E. What's next? 0.5 squared, right? Then come out of there. Plus 2 e to the point what? 6 squared. Come out of there. Plus 4. What's this? Second e to the point what? 0.7 squared. Come out of there. Plus 2. What's this? E to the point what? 8 squared. We're getting close. Plus 4. That's the last weight. E to the point 9 squared. Come out of there. And then you say plus e. So this is like e to the 1. You guys okay with that? Come out of there and close your parentheses. Now double check because old man Judge can't even see what he's doing. One of the reasons why I like some of these calculators is because it has a screen and you could double check that, right? So yeah, you guys could use your calculator on this test and just hit what? Enter, and what do you guys get? What you get is a numerical representation of what? The numerical area under the curve for a function that you cannot integrate, ladies and gentlemen. And you can approximate that to the nearest what? Let's say nearest thousandths or something, right? So you've done the following here. Here's what you've done. You've found Simpson's rule with 10 partitions to be approximately 1.4. Let's go to the thousandths position, was it? 4, 6, 3. Okay? In other words, this formula is the area from 0 to 1 e to the x squared dx, 1.463. So this is kind of just an easy kind of thing to give to people, because it was back in Calculus 1, we did numerical techniques for area under the curve, left point, right point, midpoint. Calculus 2 comes along and says, by the way, you have Simpson's rule. And they'll say, by the rule, Simpson's rule is actually better than all the others because it gets to the area faster. There's a smaller area. It really gets the area under the curve faster than even the midpoint rule. Because in Calculus 1, the midpoint rule was the rule you use to approximate the area under a curve, you know. So this is what's called a numerical technique. To integration. And it's kind of like, if you guys remember, that there was another numerical technique that we did. What's the Calculus 1 famous numerical technique that you guys did? Anyone remember? This is kind of like the analogy of the Calculus 1 very famous numerical technique. Let's go back to my Calculus 1. Let's see if we can find something in Calculus 1. Let's scroll out. So in Calculus 1, ladies and gentlemen, I know what I did. Here's Calculus 1 worksheets and videos. You go, oh my God, you did that in Calculus 1, ladies and gentlemen? Yeah, we did this stuff. Let me find it. You got volume of cylinder, this method, area, integration by substitution. Oh, there we go. A numerical technique, approximation for area under the curve. That was not I'm going to just put that there for you guys in the comment section. That was not what I'm referring to, although we did do that. It's everything I'm talking about here, right? That's why I know we did it in Calculus 1. Left endpoint, right endpoint, midpoint rule, and then some examples. You know, some of these examples we did in Calculus 1. Pretty good, right? You guys remember that? I know I do. And what did I do? You say, oh my God, Mr. Judge, what if I forgot how to do some of these things? Well, you got your tutor there, and your tutor's free. Dismiss. Only 2 likes. Oh my God, really? Only 2 likes. Here's what I'm referring to, though. Newton's method. If you guys remember Newton's method. Newton's method is like the numerical technique of Calculus 1 to some degree. And that's kind of finding, points of intersection. Without using algebra, you got to do it numerically. So anyway, I want to share with you guys that. Just go down memory lane, because now in Calculus 2, essentially, they give you the very famous Simpson's rule. Sorry, we're not even there. Okay? Now, I want you guys to note one thing. Really, your work is going to be about the partition. So take a closer look at the partition. Let's say they have you integrate from not 0 to 1. How about 1 to 4? And I got to keep it kind of simple. Maybe just x squared dx. You go, oh my God, that's very simple. Yeah. And they'll say determine S6. Now, I know you know how to integrate it. But now, where do you start with your partition, right? Remember, delta x is going to be 4 minus 1 over what number? 6, which is 1/2, right? 3/6, which is 0.5. So when you do the partition, I want you guys to consider that, right? Where do you start now? 1, that's your x naught. You guys okay with that? Because you're going now from what again? 1 to 4. So the interval is from 1 to 4. So you start at 1. That's an important thing. I've seen students miss this question because they didn't know where to start for the partition. Right? You always start with that a value, and it's going to be 1. And then, you know what you guys use? You use your what? Delta x of 0.5. So the next point will be what? 1.5. Keep adding your delta x, and then that's going to be a 2. You get a 2.5, then you got a 3. 3.5, and then you end at 4. So this is going to be x1, x2, x3, x4, x5, and x6. The important thing to do is the partition. That's where all the work really is. Okay, so after you get your delta x and after you get your xi values, these partition values, what do you think you're going to do? You can say what? S6 is, what's the formula? Delta x over 3. F of x naught. I always write it down because if I don't, I might forget it. And then I want to make sure I have my weights. 4. Okay, so remember the sequence of weights. That's a 1. You always start with 1. You always end with 1. Got 1, 4, 2, 4, 2, 4, 1. You know, and then what I do as the next step, you know what I do? I plug in what? I plug in these values. This is 1. This is 1.5. This is going to be a 2. 2.5, a 3, a 3.5, and then a 4, right? And then I want to remember what's the function again? X squared. Okay? So then very easily you can say delta x, isn't that 0.5 divided by 3 now, right? X squared, so that's going to be a 1 squared plus a 4 times a 1.5 squared plus a 2 times a 2 squared, okay? Plus a 4 times a 2.5 squared, plus a 2 times a 3 squared, right? Plus a 4 times a 3.5 squared, plus a, what's the last one? F of 4? I think that's 4 squared, right? And then this is going to give you what you guys need. So there's a little bit tediousness, but if you keep the function simple, if you keep the partitions low, you know, you can actually, you know, have some fun, I guess. But what's the main idea again? The main idea is, yes, you can numerically integrate. It's a helpful tool to have because most of the time you can't integrate anyway. And yes, the idea would you would use a computer to program, and computers do this very well, you know. So that's why, like I said, you want to take a Calculus 2 class, talk about Simpson's rule, and whenever you take your programming, you go, oh yeah, I see what they're getting at, you know. Fantastic stuff, so. All right, let's enter this in. So what is that? 0.5 divided by 3 is really 1/6, is that right? 1/2 divided by 3. So anyway, we'll put 0.5 divided by 3 again, close that. And then, ladies and gentlemen, I'm going to do some arithmetic. I know what 1 squared is. That's 1, right? And then I'm going to say this is 4 times 1.5. Here's the square key. Plus 2 times 2 squared plus 4 times 2.5 squared, right? 4 times, and then I'm going to say plus 2 times 3 squared. I know that's 9. Plus 4 times 3.5 squared. And then plus the last term is 16. So I'm going to just keep it as a 16. Okay? Because 4 squared is 16 if I go back and look at everything. You know, go back there. Back and look at that. You know, every term, double check, you know. And then I'm free to hit what? Enter. And what do I get? Area is 21, I guess. Is it 21? I don't know. Did we make a mistake? Let's see. I have no idea. One of the reasons I like to pick functions to demonstrate, what do we go from? What's the interval from 1 to 4? X squared dx. Well, we can integrate that. Isn't that what? 1/3 x cubed from 1 to 4. 1/3 was that? 4 cubed minus 1/3 times 1 cubed. Is that right? 1/3, 4 cubed minus 1. Do you guys know what 1/3 is? Or 4 to the third power? Is that 64 minus 1? 1/3 times 63. You know that 3 goes into 63 how many times? It's 21 times. So anyway, yeah, it looks good to us. Just kind of a quick little check, you know. Beautiful, beautiful technique. It's a beautiful formula, ladies and gentlemen. It doesn't take long in a Calculus 2 course. Calculus 1 course it does, because you have to teach people the left endpoint rule, right endpoint rule, midpoint rule. You have to talk about the partitions in a lot of detail. You have to remind people not everything starts at 0. Sometimes you have partitions start at 1 or 2, you know. But if you want to look at more of the detail, this is why I put in the comment section the Calculus 1 video technique and that. But I would say to you guys just need to study and do a couple of formula questions for Simpson's rule. This rule right here. Oh, I guess I have it in my... I'm dying. So I'm going to give you a Simpson's rule question, yeah? I'll give you a Simpson's rule question. If I were you, I'd look at it in a positive way. This is why. What's the positive? I'm going to say, Mr. Judge, you're going to give a Simpson's rule, right? And I'll say, yeah, let me find it. Excuse me. Oh, it's right here. Say, God's punishing you for that. Simpson's rule, right? And I think if you wanted to even see a couple of other videos on that, it's there. Yeah, it's kind of good. You know why it's kind of good? Well, that would give you, instead of asking you another integration technique question, you could just ask people a Simpson's rule question. I don't know. That's how I see it. So otherwise, you'd say, well, if you didn't do that, then you'd give people a Simpson's rule, then give people another, integration technique question, and they may not like that one. I typically find people love the numerical Simpson's rule when I grade them. That's the one that people go, oh my God, most people get right, the numerical approximation, because you just punch it in your calculator, right? So very, very little using the formula. So when I look at the book now, where is it? You go, don't use the trapezoid rule, use Simpson's rule, like, yeah. Go back here, where is that? This is like 8-7. I'm going to label it Simpson's rule. And say to you, only worry about Simpson's rule. Okay, so try a few on your own, like maybe 7 to do the odds. Just do some odds here. Just try a few. 7 to maybe 15, Odd. And don't do the others that they say. Only do what? Simpson's rule. This is really titled numerical techniques. So I would say do that because of the fact that it's just using a couple of formulas in your calculator, and then that will kill off. Instead of asking a technique and integration question, you can ask a Simpson rule question. And yeah, just from my experience, people they get that one right. People love it, and it's not really that hard. And again, I'm not going to put a very crazy function. I don't think, at all. If I look back at them, they're kind of simpler functions. But in theory, they could be a really more complicated function. But in theory, you would use, maybe you'd use a calculator. I think you'd probably use a computer. In theory, But this is all preparing you guys for the other things that you guys will see in your life. And I do recommend you guys do more and more technology. Why would I recommend that? If I would, just to give you some advice, I know you never asked for that, but I'd recommend you guys get into more programming. If you're leaning in that kind of area, why would I say that kind of stuff? Personally, I'll let you guys know. Because technology is not going away, as you guys can see. And there are people in this world that become millionaires and billionaires just using programming skills. If you guys know what I mean. It's a very practical skill to have. And if I had time, I'd go do it and take more programming classes. I have taken programming classes. And I would do more, personally. And I say that to my daughter. I say, Ashley, I think you want to do it. Of course, she hates doing programming. Anybody who's ever taken it knows it takes a lot of time. But I think it's worth mastering and getting some very good skills in programming. It makes you employable in a lot of ways. They're going to look for practical skills. They're not going to say, okay, Mr. Judge, you can do a lot of theoretical integration, and yes, you could take a derivative, but what are the practical sides of what you can do? And that's where the numerical techniques come in and the programming come in. I once had an interview at Boeing years ago. I was a kid who went out of graduate school looking for a job, right? So applied everywhere, doing everything, and I applied for Boeing. I had an interview, and it was the oddest interview I ever had in my life. I interviewed them. I show up, they're trying to interview me, and they didn't really have any good questions. They're looking at me, and I thought, there's something wrong with this picture. These guys, I don't know what's going on. So back then, I believe it was, they wanted to hire me to read a bunch of code in C++. And they said, because a lot of our programs we have here that are no longer here, they wrote code, but they never put comments about what it did. So they had a lot of code, they never put comments, they had mathematics behind it, They didn't know what they had. So they needed to pay somebody to read everything to tell them what their code actually did. Now, I didn't take the job because the date in which I interviewed and they offered me the job was like 3 months later. I thought, this is weird. These guys are like, what's wrong with those guys? I drove all the way out to like Seal Beach, And I'm like, there's something wrong with that picture. I don't know. Maybe they hired somebody right away, not me. That person quit, and they go, okay, we're going to go with number 2. Because I can think of that job being so mundane. You say, what do I do for a living? I'm reading code, telling people what it does, because the programmers never described what it did, which is what they're supposed to do. And I guess they didn't back then, as much. But I just recommend that to you guys that, so this is kind of why Simpson's rule comes to my mind. Yeah, Juan, you might. I mean, I would still, Juan, in all honesty, start to learn as much programming language, and then you should start your own company. And you can create your own whatever. Doesn't matter what it is. You're not limited. It's what your imagination is. And if you do that, then you might become a billionaire. Who knows? That's what that Facebook guy did, right? You guys know what I mean? I don't know. That's my advice, but people don't always take my advice. But ladies and gentlemen, we're out of time. I know I enjoyed myself doing what we're doing, so work on some of these questions. I'll give you guys a study guide, and I'll see you on Tuesday. So take care, stay safe, and have a wonderful day, wonderful weekend.